misclassification and we penalize with some error, so that will discuss later mathematically. So we just assume that there is a misclassification if it is moving to wrong class. So now the first idea is our first property is maximizing the margin. So margin is nothing but the distance between positive and negative samples. So let me see whether I can. So you can see that we have this is positive samples and we have this negative samples. So now the idea is how to classify this data. So the first property, as I mentioned, that maximizing the margin. So margin is distance between positive and negative samples in such a way that the data point should below this and above this. So and so we have to maximize this margin. We have to maximize this margin. And so how to do that mathematically we'll discuss more. So you can see here, for example, if I say that this is W transpose X plus B, this is just an equation of W transpose X plus B less than equal to 1. Okay. Positive class and negative class. So if it is negative class and this is positive class. Okay. If I want to just maximize this distance between positive and negative samples, so and we are maximizing the margin, so maximizing the margin just the distance. So distance, if you take the distance between positive and negative samples, so essentially, so it is coming to be 2 upon norm of W. So essentially, if we have, you can see here that if we have W transpose X plus B equal to +1 and -1, so just we maximize. So essentially, we have 2 upon norm of W. So we are maximizing this margin subject to the condition, as I pointed out, that the data point should below this and above this. It means that W transpose X plus B, it should be greater than or equal to +1 class, and it should be below -1 class. So you can essentially combine this one and you can just say yi W transpose X plus B greater than or equal to 1. Here yi is +1 -1 if you combine it. Okay. So this is the first idea, that we are maximizing this margin subject to this condition. So the first formulation is maximum 2 upon norm of W subject to the constraint yi W transpose X plus B greater than or equal to 1. Okay. So now to move ahead to max, you can say that if we just say maximum 2 upon norm of W, so you can equivalently write, if you means you can say that if as soon as you are minimizing this W, right? So then this whole terms is maximized. So essentially you can say that equivalently you can write, or equivalently you can also write this is norm of W square by 2. Okay, and subject to the condition. Now in the soft margin, as I have given one example, that if there is a misclassification, means the data point of this class is coming here, so then it is penalized with some error, like suppose xi1. So, and there could be more than one misclassification. So we sum up in the objective function, we minimize W plus C. C is a parameter that control the overfitting, and we sum up all the misclassification error like xi1 plus xi2 plus and so on xi(n). Okay, so we can see here that if we say the difference between hard and soft margin, so we simply have this is as I mentioned initially, that W half W transpose W subject to the constant yi W transpose x plus b greater than or equal to 1. So, and in the new formulation as we discuss here, so this is the objective function and subject to this constraint, and where xi I greater than or equal to 0. Okay, so now again I'll discuss mathematical way later. Initially my plan is to just visualize the concept of SVM. So you can see that when we solve this formulation or this formulation, so depending on the kind of formulation, so when we find out its dual, so you can see that this is coming like this formulation. Okay, so one observation here, since xi is the trailing data points, so you can see that this is appearing in the form of inner product. Here xi transpose x. So this is nothing but it belongs to a number. I hope you know the concept of dot product in vectors. Okay, so for the linear case, nothing to worry. So here, my point to highlight this here is it will help us to understand the concept of non-linear case, means the difficult class for classification problem. So let me come to with this example, and you see the first one is very simple. In the left, you can see that we have red data points, and the right hand side we have blue data points. So you can see that if I want to draw a line in the middle, so it is nicely classified. There is no problem. But what happens if I put red, blue, and then red? Okay, for this example, so we cannot classify this example linearly. But in R, means in one dimension, we cannot classify this one. But if you move to higher dimension like R2 to R2, so we nicely classify. How to do that? So you can say that if I map from x to x square, if we have a function of fx equal to x square, so you know that this will be like this. You know well about this fx equal to x square. Okay, so now if we are using from R2 to R2, means one dimension to two dimension, so you can say that the same data with this function, you can say that the data points will move up, and you can draw a line in the middle, and you can say that the data is linearly separable. So essentially, my idea is just to show that if the data is not linearly separable in one dimension, then it could be linearly separable in higher dimension. It could be separable in 2 dimension or 3 dimension and more. Okay. Like you can say that this is a very difficult example in the left side, this one. You can say that we cannot draw a line linearly. So what we do, so this is, we are moving to the second property of SVM. We already discussed about maximizing the margin concept. Now we are moving to the kernel trick, means how the kernel concept is coming. So as I mentioned that we can see that data points are, if not linearly separable in one dimension, it can be linearly separable in higher dimension. So with this idea, we are moving to higher, more dimension. You can see that in the left side, this data, we cannot draw a line that can linearly classify. So what we do, we transform this data to higher dimension space with some map. So you can say that we use, you can write that, suppose this phi, and this is Rn to Rn. And you can see that the left side is some n equal to 2, means R2, and this could be in some dimension, and here m is strictly greater than n. Okay, so with the same idea that we map the input data. So this is input data. We using this phi, we map this data into some high dimensional space, so such that the data is linearly separable in some dimension. You can see here in plane, you can see that data point is linearly separable, and we can draw a line. Okay. So essentially, we can see one example like this one, and we can say that we can write k equal to phi transpose phi with this polynomial kernel example. So, and linear kernel is nothing but, you can say that if I write xi transpose xj, so this is nothing but some k. And you can say it's a linear kernel. Okay. So, and there are many kernel functions available in the literature. You can go through, some of them are mentioned here, and a lot of theory available in the literature. And you may have, if you're working in SVM and you are the learner of SVM, so essential idea is coming in our mind, choosing a kernel. So choosing a kernel as can say an open problem, that one cannot say to me or to us that you have to use only this kernel function. So yeah, there are theory and literature available numerically. If we look at the comprehensive evaluation numerical, so some conclusion are coming, but in general, it is difficult to say that this kernel function is best. So people are working on multiple kernel theory. People are using ensembling of kernel functions. Means suppose we have 10 kernel functions like K1, K2, K10. So people are using like weighted kernel, some different kind of linear combination of kernel functions that usually give better results. So, and but what we see in the literature, especially in the evaluation part, numerical part, what we observe in general, that this Gaussian kernel function RBF, this is performing better in many cases. So now you can see that if you recall linear case, so in place of kxi xj, it was simply xi transpose xj. Okay, so but when we are talking about in nonlinear case, so you remember that we just transform the data from input space to some high dimensional space such that the data is linearly separable. So essentially when we are solving the problem, so here in place of this k, it is coming like phi xi transpose phi xj. Okay, so what happens, this is also again a number. Okay, so now let me just give you some clarity. Earlier we were working on linear SVM, and it was easy to solve, and you see that dual problem is just some dot product of vectors and we solve it. But when we are talking about the nonlinear case and we solve the dual, and again we see that in place of xi transpose xj, and we are getting phi xi transpose phi xj. So this is again a number. Okay, so the point here is that we are mapping this input space to high dimensional space. So the essentially idea is that we cannot and we do not need to know the nature of phi. You see the beauty of SVM here. So we are working on a very high dimensional space, and with the help of this phi, even though we do not need to know the nature of this phi, it could be of any dimension, means m and n. So why? The reason is, you can see that while solving the problem, solving the SVM, solving the optimization problem, we are just see that this is nothing but a number. So we do not need to know the nature of phi. So we are working in high dimensional space, but essentially in linearly. So you can see here that SVM locate a separating hyperplane in the feature space and classify points in that space. Then second point, it doesn't need to represent the space explicitly, as I pointed out, simply by defining a kernel function. And here kernel function play the role of dot product in the feature space, high dimensional space. Okay, so far I covered some geometrical perspective, and now let me just come back to discuss some theoretical more concept here, and how we are getting this dual optimization problem. So those things we'll discuss now in the next 10 minutes. So essentially you can see that when we are talking about linear SVM, so we have training data T, x1, y1, x2, y2, xl, yl, and where x1, x2, xl are some input data, and yi are class labels. Okay, And since here y is -1, 1, it means that it is a two-class data initially, and we can move to multi-class classification problem. Okay, so the idea is to find a separating hyperplane between positive and negative classes. Okay, and data points which lie on the planes termed as support vectors. And this is a geometrical representation of SVM. This is more clear. If we compare with the previous figure, so you can see that we have a positive class and this is negative class. So the first property is maximizing the margin. So this is the distance between positive and negative samples. It is coming out to be 2 upon norm of W. So we are maximizing this margin. Essentially, equivalently, we can say we are minimizing W. Okay. So, and let me just see the linear formulation. Already discussed this part. So how to solve this problem? So we are minimizing W, and plus since it's a soft margin, misclassification error are there. So we just sum up in the objective function, xi1 plus xi2 plus and so on xil, subject to the constraint that the data point should above class +1 and below class -1. Okay. So the idea is how to solve this problem, how to find out the dual. So here we will discuss. So let me discuss a more general way first. So suppose we want to minimize a function fx subject to the constraint gx equal to 0. So essentially we have one function that to be maximized or minimized, and we have one constraint, and this constraint is essentially equation, equality. So the necessary condition for such kind of optimization problem to be a solution such that the partial order derivative of this function, objective function, plus alpha times gx, here g is constraint. So here alpha is a Lagrangian multiplier at x equal to x naught should be 0. And the constraint is there, gx equal to 0. So what happens since we have one function here and one constraint? Suppose we have more than one constraints, multiple constraints. So the only change here is that we just take the partial order derivative of x plus this one. So it will be alpha 1 g1x plus alpha 2 g2x plus and so on at x equal to x naught equal to 0, and all the constraints like g1x equal to 0, g2x equal to 0, and so on. Okay. Now to move ahead, if we have the inequality constraints, so in this case alpha I should be positive, and this condition should satisfy that partial order derivative fx plus summation alpha I gi at x equal to x naught and gix is less than equal to 0. So here the function fx plus summation alpha I gix is also known as the Lagrangian, and we simply want to set its gradient to 0. For example, let me come back to this problem. So how many of you are getting, so is there any problem, any doubt so far? So I want to know, because for me and in my previous experience, it's quite a simple thing, but I'm not sure about you. So please let me know if I need to skip those things or discuss more. Anyone?
Yes, participants, we ask you to please give your opinion.
Yeah, your feedback
He
will
is
be very
writing,
important.
somebody discuss, they are saying discuss more. So,
Oh, great. So you can see here we have this optimization problem, and we want to solve it, and how to find out the dual. So you can see that this optimization problem, essentially we have objective function and we have inequality constraint. We have objective function, inequality constraint. So it means that we have to use this one. So the same we will use here, that this is, you can say this is function fx, and you can make this one is gx, greater than or equal to 0, you can write. Okay, you can keep in the left side and you can write. So we are just writing that this is fx minus summation this beta I xi I and minus summation alpha I. So here alpha and beta are Lagrangian multipliers, and the same thing is we are writing. And then I think I skip. I have written that we differentiate with respect to w first, and then d, and then xi, and using KKT conditions, and finally we are getting this one. So essentially what happens when you take the partial order derivative of this one, so you can say that you are getting like partial order derivative. Let me just suppose I want to find out del partial order derivative with respect to w. So the first one for this term, it is nothing but this will be w only, and nothing is there, it is 0. So and will come back here. So essentially will come minus some alpha I yi xi, and this is equal to 0. Similarly, you will do for del L over del B, del L over del Xi, and you simplify and put again value of W, and you put those things. So finally, you are getting this information, this dual form. So it's quite simple when you are getting this one, and this is same summation alpha I yi equal to 0. So what happens, you can see that the data points here are appears in the form of inner product. Okay. So if the training data are not linearly separable, to enhance linear separability, the original input space map into high dimensional dot product space called the feature space. And you can see for the linear case, so this is inner product xi transpose xi. So we can do the same thing for the non-linear case. So one important note here, as long as we calculate the inner product in feature space, we do not need to explicitly mention the mapping. Okay. So there are a few properties of a kernel function that it needs to satisfy the Mercer theorem. So please go through this one. So detailed information you can find out that the K should be positive definite. So now if we are moving for the soft margin and for the nonlinear case, so in the nonlinear case, the only change is in place of xi, this is of phi xi. Okay, and when you solve it, so essentially in place of x right x transpose x, it is now phi transpose phi. Okay. So some benefits, some drawbacks for the SVM, that few things are written, many things are not written. So this is training is relatively easy, no local optima, unlike in neural network. It scales relatively well to high dimensional data. trade-off between classifier complexity and error can be controlled, like we are using parameter C. So, and some concern that choosing a good kernel function and complexity is very high. So why complexity is very high? So you can see that we have an objective function and subject to the constraint of two classes. Means one constraint corresponding to +1 and another is -1. So we are now we'll try to resolve this issue also in this lecture, that we will discuss a formulation that will handle this issue, and also we'll try to address this sensitive that SVM with hinge loss is sensitive to both label noise and feature noise. So we already have developed several model. You can look at some pinball general twin SVM. So essentially what we did, that we are simply using pinball loss function with original twin SVM problem. So, and we know that the pinball loss is insensitive towards noise. So that concept is really cited a lot. So now moving ahead, first I'm thinking to discuss the concept of twin SVM. So we already discussed what is SVM, and now I'm moving slightly up, or I can say that some advanced formulation that address the issues in SVM. As I mentioned, that complexity is high. So usually we say that, okay, in the next slide we'll discuss mathematically, so how it is efficient algorithm twin SVM. So twin SVM is computationally efficient model for classification problems. So it performs classification using two non-parallel hyperplanes instead of a single hyperplane as we see in original SVM problem. So let us consider a binary classification problem to classify data points belonging to class 1 and -1 that represented by matrices A and B. And here L1 and L2 data points belonging to class 1 and -1 in n-dimensional space. So let me now discuss first the formulation and then explain what exactly twin SVM is. So you can see that the linear twin SVM, it looks for a pair of non-parallel hyperplanes. So like W transpose X plus B equal to 0 for positive and negative class. And each hyperplane is close. The idea of twin SVM essentially that each hyperplane is close to the data points of one class and far from the data points of the other class. So you can see the formulation here 2 and 3, and let me try to explain 2 and 3 what exactly we are doing. So you can see here equation 2 and 3, and if you recall original SVM formulation, so we were having one objective function and two constraints, means constraint of both positive and negative class. So, but this twin SVM formulation, it find two hyperplane, one for each class. and it classify points according to which hyperplane a given point is closest to. So here the first term is the sum of square distances from the hyperplane to points of one class. Therefore, minimizing, it tends to keep the hyperplane close to points of one class, say class plus one. And here the constraint required, the constraint require the hyperplane to be at a distance of at least one from the point of other class, say class minus one. And here we have set of error variable is used to measure the error whenever the hyperplane is closer than the minimum distance one. So essentially the second term is the sum of error variable, and this attempt to minimize misclassification due to points of belonging to class minus one. So if I just say in summarize, here twin SVM are composed of pair of quadratic programming problem such that in each QPP, like I can say this is QPP1 and this is QPP2. So it's a comprise of a pair of quadratic programming problem such that in each QPP, the objective function correspond to a particular class and constraint are determined by pattern of other class. So it means that when SVM give rise to a smaller size QPP. So if I, as I mentioned that if I talk about its computational complexity, so usually we know that the complexity of SVM is order of big O M cube. So M is the size of training data. Okay, this is for SVM. But what we see in the case of twin SVM solve two problems, like mentioned here, 2 and 3. So each of which is roughly half size, like M by 2 and M by 2. So we just, this is not always possible when the problem is coming of class imbalanced learning. Okay, but we just think that suppose we have two class and 50% class samples. So we see that each of which is roughly size M by 2. So it means that if I compare that this is M cube and this is 2 times if we have M by 2 cube for one QPP, another QPP. So this is roughly 4 times faster than standard SVM. Okay. Any doubts so far? Okay, I think so. No doubt. So I think rather than moving ahead, let me just discuss few things about clustering problem. So in machine learning, we know that's a part of AI where we study some advanced computer algorithm that improve by themselves with the idea with the data provided by finding some pattern or trained in the data. So machine learning can be further classified supervised, unsupervised, semi-supervised. So here the idea is to discuss unsupervised learning, where labels are not known to us and there is no prior knowledge of the class of a particular data point. So clustering is an unsupervised learning technique that involves the grouping of data points and discovering the relationship between them. So given a set of data points, a clustering algorithm can be used to classify each data point into a specific group. And this technique makes clusters among data point by observing similarities and dissimilarities between them. So there are different kind of clustering algorithm. So now I think these things are simple. Let me just give the idea of twin SVM geometrically. So you can see that rather than having a supporting parallel hyperplane, so in twin SVM we have a non-parallel hyperplane. So we can see that uh, we have, this is one QPP, this is QPP1, and this is another QPP. So we have two smaller kind of SVM problem, as I discussed theoretically. You can see here. So now let me discuss how to move towards clustering problem. So we discussed what is twin SVM, already discussed here. This is twin SVM formulation. Now I'm thinking that the same formulation, how to move and how to write for the clustering. Okay, unlabeled data. So you can see that the idea of twin SVM, when applied to clustering to clusters, to cluster this data samples into k classes by approximating k planes for k classes. So we can write the formulation of twin SVM for clustering problem. It could be written as here like this. So you can see the equation 1 here, norm of xi wi plus bie square plus ce transpose I, subject to the constraint. We have mod of xi cap wi plus bie greater than or equal to e minus xi. So you can see some geometrical interpretation. Suppose we have, this is based on similarities and dissimilarities. So we have class samples 1, class samples -1, and this is a center plane. So based on the similarities, we have three different clusters: cluster 1, cluster 2, and cluster 3. Okay. And then we can solve. There are several people have several ways to solve the problem. So this twin SVM for clustering problem was used, this CCCP, that is called convex concave procedure. And not going to further details. So we just simply solve exactly in the same manner as did for twin SVM. So here you can say that the matrices appear in the dual formulation may not always invertible. So what we do, we add extra regularization term in here, like in place of H transpose H, we just add some delta. Okay, and here delta is some small positive number. Okay. And the same idea is introduced for twin bounded support vector machine for clustering problems. So in twin bounded, what they did, they introduced extra regularization term in the objective function, and it was same. Okay. So due to this, the issue mentioned here, it will automatically resolve. You will see that when we look at the dual formulation, so in place of H transpose H, it will be look like this one. So let us see. We are introducing extra regularization term in the objective function. When we solve this problem, you can see that this is coming like this: hi transpose hi plus c. I think it should be c. C is this one. Okay. And this is our recent contributions for us using pinball laws functions. So the main advantage is to overcome the issues of noise sensitivity in the original twin SVM problem, twin support vector clustering problems. So using this twin SVM, using this pinball laws. So we have this pinball loss function. Due to this, we have an extra constraints. And you can see here from this one, when this tau, when tau is moving towards 0, then you will see that this is xi I, this j plus 1 is moving towards 0. And it's moving towards, it is moving towards greater than equal to 0. So essentially what happens? So when tau goes towards 0, so this is, it will degenerate to the original twin SVM clustering problem. So you see that in the original twin support vector clustering problem, this is same, and extra is this xi I j plus 1 greater than equal to 0. Okay, when tau goes towards 0, so it is coming. So essentially, that will be a particular case of this pinball twin support vector clustering problem. So now there are some limitations. Although pin TSVC is noise insensitive around decision boundary and more stable for resampling of data samples, and but the ill conditioning of the matrix in the usual is in the dual is again a problem. So then we use twin bounded support vector clustering concept. So using pinball laws, using pinball. So you can see that when we are using pinball laws in the twin bounded support vector clustering, so both issues will resolve. Means that noise sensitivity issues will resolve, plus the singularity issues in the matrix will resolve. You will see that we have this optimization problem. We include this as TBSVC. So this is nothing but this is TBSVC using pinball laws. So using that, you will see when you find out the dual formulation, you can see that the matrices appear in the form of in the non-singular form. So no issue of singularity. Okay, so I think then we moved some sparse version. So I think please have a look from our papers. Now I'll move towards a few more things towards applications. Okay. So now I think I can take a 5 minutes question answer here. If you have any doubt so far, so because my idea is to discuss two things. Two things are remaining. One is to show the applications of our work to Alzheimer's disease and epilepsy. Okay. And the second is how to handle the issue of the larger scale data. When the data is large, how to handle that. So any question from anyone? Bataiye please. Anyone? So I hope that you understand all these theory. So let us move ahead to discuss a few applications in the next 10 minutes. So, and whatever I'm discussing now, it is based on the universum data. So what is universum data? So universum data, if you remember, if you know, when a teacher is coming to class and discuss some idea, suppose he is discussing like eigenvalue, okay, eigenvalue, eigenvector, or some diagonalizing, any concept, okay. So in addition to the concept given in the book, he tried to explain with some extra information, with some examples, so that you can understand better. So it means that you are getting some extra information, advanced information about the concept. So essentially, the things is coming up in the same manner that we are using this universum data, means information about the distribution of the data. So we have, you can see that epsilon insensitive tube here. So only this part, up to this part is universum data, and this is class 1 and -1 samples. Okay. So rather than moving and discussing those things, let me So you can see that in order to incorporate knowledge about the data distribution, we use universum samples. So, and the resulting universum based algorithm use this prior information about the distribution of data. In a particular algorithm, here we are using recursive elimination of features. So just to get the better feature selection. Okay. So now let me just discuss about Alzheimer's disease data, how we are working. So this data is publicly available and we obtained from ADNI website. You can see adni.loni.usc.edu. So, and this is done and launched by PI Michael Wenner. So the main objectives of this data is to analyze the effectiveness of neuroimaging techniques like MRI, positron emission tomography like PET, and other biological markers and clinical neurological tests to estimate the onset of AD from the state of MCI, mild cognitive impairment. So there are other data like OSIS data also there, and other data also. So it depends on whether you need more data or less data depending on your kind of formulation. So, and for evaluation, we use some accuracy, sensitivity, specificity, F1 score, and a few others. These are some of them. So like based on our proposed idea, so we just used the CN versus. So CN is healthy patient, healthy person, control normal, and AD is Alzheimer's disease. So this is a more simpler way. So why this is a simpler class? If a person is AD, I think if you remember about Alzheimer's disease, this disease we came to know after 60 or 65 years, when the disease is at the advanced stage, and this disease is not curable at today, and there are more than 35 or 40 million people. So and it is going very high, but no cure. So the idea is that, is there a possibility to develop a automated model to diagnose AD at the early stage? If we are able, so essentially AD, Alzheimer's disease, started at 30 or 32-year age. If we are able to know that the disease progression started at 30 or 32-year age, so there are possibilities by the doctors to stop uh, that disease. But when we came to know at 65-year age, so that time that disease is non-curable. We cannot do anything. So that's a really very difficult difficult research problem. So we have tried our best, and we are successful in developing few machine learning models for AD. So and we'll discuss few of them today, and if you are interested, please go through our recent papers. We have developed based on deep variants for Alzheimer's disease. So please go through those papers. It's available on my homepage, available on my Google Scholar, everywhere. So you can see these are just illustration of reduced gray matter voxel. These are obtained after feature elimination process. And the left side is proposed for the proposed model, and the right side is the baseline model. Again, for CN versus AD, means healthy and AD, Alzheimer's disease. And these are few numerical experiments. Okay, and more experiment here. And this is also again CN versus AD. Just to check, when we are considering features, 75%, sorry, 50%, 30%, 20%. So what we observe for the proposed case, if we have more features, so we are able to get better accuracy. More information, more advantages. So now this is EEG signal classification using a universum based SVM. So essentially, so far we are using EEG data which is available publicly. So but now we already have procured EEG wireless recording system, and developed one lab here at IIT Indore. So we are able to record the original data for this, and we are able to do some work in this direction. So you can see this is a different type of EEG signal, like healthy. The first one is healthy control, the middle one is interictal, and the last one is ictal state. So some information about the data set. So EEG data set is taken from this one, Andrei Zizek, which is available online. And there are 5 sets like Z, O, N, F, and S. So, and each set contains 100 single channel EEG signal sampled at a sampling rate 173.61 hertz and of 23.6 second duration. And here this set Z and O are surface EEG recording of 5 healthy volunteers with eye open and closed respectively. And the set N and F are recording of 5 patients in the interictal state And the region of recording is the hippocampal formation of the opposite hemisphere of the brain in N, and the epileptic zone in F. Okay, and the set S is for ictal state consisting of seizure recording from all the recording sites exhibiting ictal activity. And the mode of EEG recording is intracranial for N, F, and S. So usually there are few steps for EEG signals recording. So we just choose a feature extraction technique and extract the features from training data consisting of healthy and seizure data points. Then we extract the features from universal points which are taken from seizure-free data set. Then we use any to reduce the dimensionality. We use some technique like standard technique is PCA or maybe CDR. Then we train the model using training data with the universum and then test. So we have done some experiment, and this paper was published in Expert System with Applications and is highly cited of that journal. Means it is in the category of high cited papers of Expert System with Applications since 2018. So I think this is what I thought for this one. Now I'm moving to discuss few problems for the large scale data. Okay. So any question again?
Yeah, Dr. Tanveer, am I audible?
Yes, please.
This is Ashwin Yadav here. I have a question with regard to application of genetic algorithm in general, in particular, like in your optimization problem, and in general when we are doing back propagation or loss function estimation. So is there a scope for use of genetic algorithm, considering it is a global optimization method, maybe giving better results than SGD, standard approach that is used?
I never tried, but there is a scope for improvement.
Because this is a general point, I thought maybe a good idea to tweak. It's general applicable to all machine learning and deep learning approaches.
Yes.
Because it gives good results in tracking, etc., object tracking, in terms of target tracking and all. One has tried to use it, so I thought I'll just pose this question.
Yeah, I agree with you. So, but need to do that and see.
Okay.
I never explore this one.
Yeah, but I think you find that there is some merit in the possibility of its use, right?
Sure.
Thank you.
So now my last objective of today's talk is moving towards handling larger scale data. So first I'll discuss with a very basic and old algorithm, least square twin SVM. If we compare with the simple twin SVM, so the only difference is just in place of inequality, we have the equality here and here. So, and no condition on xi and eta. So in twin SVM, xi and eta greater than or equal to 0. So this condition is not here, and inequality replaced with equality. This is the only difference here. Okay, and unlike twin SVM, we are solving here system of linear equations. It's easy to solve. You can what you do, you just put the value of xi in the objective function, value of eta from constraint in the objective function, and you can directly solve it. No need of any optimization toolbox like QPP and all. Okay. So now moving towards this problem, improved twin SVM. So the advantage is this new formulation. It was published in not a very good journal, but idea is really amazing. This IT-SVM, improved twin SVM, reformulate the primal form of twin SVM to make it feasible for large scale data. And this IT-SVM minimize the structural risk, which results in improved generalization performance of the model. And IT-SVM avoid the computation of the matrix inverses, while as other given baseline model need to calculate the matrix inverse, which is infeasible for large scale problem. And finally, IT-SVM doesn't have to deal with the kernel generated surfaces, unlike we look for baseline model like twin SVM. So here we are just using kernel trick directly. So I'm just using one formulation nonlinear case. So essentially, if you look at it, so this formulation and twin bounded SVM formulation, both are exactly same, nothing changed, 100% same. Okay, so this formulation, and it was, I think, published in 2011, this TBSVM, and this paper came in 2014. Okay, this formulation is same, but the way they are handling, as you will see that is really amazing. The way of solving. So what they are doing, they are solving this problem in such a way that they are considering this one as a constraint. The first thing they are considering as a constraint. Second, they are keeping this one in the Lagrangian function. So you can see that they are keeping as a Lagrangian function here additionally. So what we are doing all these by simplifying by partial order derivative and all. So while solving, you will see that W1 and B1 and this quadratic programming problem, dual form, and W1, B1, and here Q cap. You see that Q cap. Anywhere you will not find that you need to take the inverse of the matrices. So that invertibility issues automatically resolved. You can see from here 19, 20, 21, 22, and 23. So it's a very small change in the idea, but completely change the nature of the problem. So now we are able to apply large scale data because what happens if we have the size of the data is very large, means in the thousand or lakhs or millions. So then to take the inverse of a matrix is again a lot of calculation and difficult to execute in normal machine, computing machine. Okay. So this is our first effort. And this is large scale least square twin SVM. I already discussed twin SVM, already discussed least square twin SVM. I already discussed this improved twin SVM. So with those ideas, my student, during her master thesis, Shilpa Sharma, she is now in Germany for her PhD. So develop this idea for large scale data. So what we are doing, we are introducing the idea in the least square based. So we are handling these two issues, that competing inverse matrices, which may lead to suboptimal solution in some cases and make them ill-suited model for large scale data analysis. And second point, that we directly employ kernel technique. So, and the proposed model is least square. So, so it means that when we look for the non-parallel hyperplanes for samples, so we just use different Lagrangian functions, so we can obtain pair of unconstrained optimization problems. So you can see that we have the formulation here. So it's a least square version. Equality constraints are there. You can see. And when we solve this problem L, and then take the partial order derivative with respect to W1, B1, eta1, zeta1, alpha, beta. So we finally solve it, and you can see that W1, B1, and this Q cap, and this one, you can see that invertibility issues are removed. So we are able to handle that invertibility issues in this formulation. Okay, similarly for non-linear cases also. So we did for the non-linear case, and you can see that another, as I pointed out, rather than having kernel generated surfaces, we directly implemented. So rather than writing AW1 in linear cases, we just writing phi A. Phi AW, you can see here. So it means that if you just put in place of phi A is A, so it is nothing but it's a linear case. So, but this is not true for twin SVM or twin bounded SVM. So they have kernel generated surfaces. It means that if you change the kernel, so that non-linear kernel is not equivalent to the linear kernel formulations. So that issue is also resolved. So in the similar manner we have done. So we do not need to calculate the inverse of the matrices. Moreover, we can easily degenerate it to linear formulation by using linear kernel functions. And similar to linear case, non-linear case also move to the unconstrained optimization problem. So now I'll try to show you some experiments here. So the idea is that we develop this algorithm for the larger scale data. So we have seen for the smaller size data, and we can see that for the smaller data also it is performing very well. You can see that overall win-tie loss here on 15 data set it is performing overall winner, and on type on a 4 data set, and loss only on 4 data sets. And average rank is also best for the proposed formulation. This is last column is proposed formulation. Okay. So now when we go for the non-linear, so for the non-linear case, even results are far better. You can see average rank as better if we compare with the linear case. This is 1.65. Okay, so now when we move to the large scale data, we used a few data like more than 1 lakhs, but what happens on the same machine, same competing machine, we implement all the 4 algorithms: TBSVM, Twin SVM, RLST-SVM, and the proposed algorithm. So what we see that the baseline, these first 3 columns, they stop working when the size of the data is increasing. However, the proposed algorithm works fine. And if you compare with the time also, you can see for the connect data, the first 2 algorithms, TBSVM and Twin SVM, stop working. But when we look last 2 algorithms, so you can see that it is taking 280 seconds. and it is taking 23,000 seconds. You can see the difference. So we can say that our algorithm is more efficient. Okay. So I think I have not covered one. Yes, yes. So this idea, another idea using pinball laws. I already discussed one formulation using pinball laws functions. So we developed this for the large scale data, and this work is already published in machine learning. So machine learning is considered to be the top journal in machine learning area. So what we did essentially, so using the last problem we discussed, so we also use the pinball laws functions to make the to address the issue of insensitivity to noise. So, and it resolve all the issues at the same time, means calculation of the large matrix inverses, and it is more stable for resampling and direct kernel trick. So those issues are resolved in the same formulations. So this is our proposed formulation. So, and when we solve this problem, linear and non-linear cases, you can see the experiments. These are the experiments on the some large scale data. You can see the time. We just compare the time, and you can see that the proposed idea is performing very well. We also did the same thing for a smaller size data. For the smaller size data is also performing well. Okay. So we try to address more issues also. So this paper is also accepted. Let me see where it is accepted. This is now recently accepted IEEE transactions on cybernetics. This is also a top avenue in our area. So, we are addressing the issue of class imbalance learning here. So this is a motivation of this problem, that analyzing the existing formulations, there are several shortcomings, that the baseline model, including this one, you can see this one. This is a class imbalance in learning formulations. In this formulation also matrix inversion is there. So how to avoid that? So this create the issue in apply to the large scale data. Okay. So, and these formulation implement the empirical risk minimization principle. So we address this issue, and the proposed idea is implemented structural risk minimization principle, and the matrices appear as always well conditions. Okay, and we solve linear and non-linear case separately in this case, in the proposed idea. And this proposed idea handle the class imbalance learning problem, unlike baseline models. Okay, so this is the formulation. Sorry, this is in IEEE this already accepted in IEEE transactions on fuzzy system. I confused with another paper in IEEE transactions cybernetics. So you can see the essential difference in 2-3 steps. One is introducing this concept of fuzzy and implementing direct kernel trick, and introducing extra regularization term in the objective functions. These are the changes in this proposed idea. And we used this fuzzy weights, fuzzy membership functions using the 69. And here Z is 1 upon 1 plus IR. IR is imbalance ratio. So you can see that, for example, we have the COVID case. Okay. And if we compare with COVID with non-COVID, and the number of COVID cases is small compared to the healthy person. So it's a highly imbalanced situation. So we have to write the formulation in such a way that handle the issue of this class imbalanced learning. So when we solve this problem, so you can see that all those issues are resolved for the class imbalanced learning, invertibility issues, and all. So we use SMO algorithm for this one. And these are a few results. I think these are small size data, and these are the large scale data. So you can see when we are working on the large scale data, so the baseline models, so all these are baseline models between SVM, LSD SVM, FTW SVM, RFLSD SVM, and this is our proposed formulation. So you can see that all the baseline models failed when we increase the size of the data set. However, the proposed idea performing very well. Even if you compare with these one, you can see the timing in seconds. Proposed takes 448 seconds, and the baseline takes 6,000 seconds on the same machine. So if you are comparing timing or accuracy, so it is very important to have the same machine and same configuration, same setup. Only then you can validate your proposed algorithm. Okay, so any doubt so far, just let me know.
Thank you, Dr. Tanveer. Participants, if you have any questions, please feel free in asking questions. Please raise your hand. We will unmute you, ask you to unmute yourself.
Because in another 5 minutes. Yes, please.
Can we get, so this you will be getting the support material. I request Dr. Tanveer to please share his slides. You will be getting, we have been telling all the participants, they keep on asking the same thing. So we request on behalf of the participants to please share your slides.
Okay, sure.
Thank you. Any questions? If there are no questions, I think you have been telling about these, asking questions, and people have been asking questions. I don't see any raised hands.
Okay.
So, yeah, so.
So in that case, in a few minutes, I'll discuss a few announcements from my side.
Sure.
In another 2 to 3 minutes.
Sure.
So,
please take.
We are working on several research projects in our lab.
Yeah.
So if any of you are interested in these projects, you are welcome to contact me in my email. Usually we are working on machine learning, deep learning, and applications to healthcare. Please go through our homepage. I would acknowledge to several funding agencies to support our work so far. So, and I would like to invite to submit your new ideas related to these special issues you can go through this cognitive computation Springer journal and engineering application of artificial intelligence Elsevier journal. So both are highly impact, and you can see if any of you would like to submit your paper related to the theme of these special issues, we are happy to consider. Okay, now to move ahead, we are inviting you to MISP, Machine Intelligence and Signal Processing Conference. So we are the founder of this conference. We started here at IIT Indore, and this time the fourth series, and it will held from March 12 to 14 next month at NIT Raipur. So you are welcome to attend this one, and happy to announce this ICONIP 2022. So it is going to be scheduled here in India after 18 years. It was scheduled in 2004 in ISI Kolkata, and after 2004 now in India. I'm one of the journal chairs of this conference. It's a core rank A conference. Okay, so thank you so much for your attention. So this is what I feel to share with all of you. And my email is here. You can see. So thank you so much.